Hello viewers, we learned about tensile testing in the last episode and the related terms for tensile testing and also the load elongation curves, and by analyzing these curves and we have learned how to actually predict the properties of the textile materials. And today we will look at the principles underlying many machinery for testing tensile strength testing of fibers, yarns and also the fabrics. So, tensile testing of textiles is an important area in textile testing, as many characteristics of the final textile products depends on the strength. So, several tensile strength machinery are in vogue today for testing the fibers, yarns and also the fabrics. The fibers are tested to know their suitability for making them into yarns or for desired tensile characteristics. Instruments used for tensile testing of textiles work under conditions of constant rate of loading, constant rate of extension, constant rate of traverse. And various principles that are underlying many of these machinery are, one is the pendulum lever principle, in which the instruments are available for testing of the fibers and fiber bundles and also single yarns and Lee yarns and also the fabric. And we take the balance principle, and the instruments are available for testing of single fiber, fiber bundle and also the fabric. And then we have another principle, that is loading by springs, and in this the instruments are available for testing of the single fiber and single yarns and also the fabric. And then the inclined plane principle is another one, and in this we have instruments for testing of the single yarn and also the fabric. Then another principle is ballistic or impact testers, and in this we find that the instruments are there for testing of the fiber bundles, yarns and also the fabric. And another very important principle which is in vogue today is the strain gauge or transducer, and this is used for testing of the yarn, and it is also multi-purpose. Many other things can also be tested under this particular principle. And one more principle is the constant tension winding, and it is used for yarn which is running to find out the number of breaks. Then coming to the first principle, that is the pendulum lever principle, and it works with constant rate of traverse. The loading of the specimen is carried out by a pendulum system which is mounted in such a way that it rotates about its center of gravity. When you look at the figure, consider two jaws, that is upper jaw J1 and there is a lower jaw J2. So, a specimen is clamped between these two jaws. The clamp J1 is attached to a steel tape which runs over a small pulley of radius r. The lower jaw J2 is given a constant rate of traverse in a downward direction, perhaps by a screw mechanism. The small pulley is pulled round, and in doing so swings the pendulum P from the vertical, and so let the mass of the pendulum be m and its center of gravity at a distance b from the pivot of the small pulley. So, assuming the specimen to be inextensible and an absence of any dynamic effects, let us consider the conditions obtaining at any chosen instant when the angle through which the pendulum has moved is theta radians. Taking moments about the pivot of the small pulley, we can say that the force into the radius is equal to the mass, the center of gravity into x, that is also equal to mgr, that is mass, center of gravity and the distance into sin theta. That means the values of mgr and r are mostly constant, and therefore, we can say that F is proportional to sin theta. Since the force F is acting on the tape, it is also equal to the tension in the specimen. Thus, the tension in the specimen is proportional to the sine of the angle through which the pendulum has been swung. The effect of extension on the loading of the specimen cannot be ignored, and the rate of loading and the time to break are influenced by the extension of the specimen. the velocity of the upper jaw is less than that of the lower jaw by an amount depending upon the extensible properties of the material. So, by adjusting these two, the effect of this extension can be overcome. When the specimen breaks, the pendulum will have an angular velocity depending upon the rate of traverse and the extension of the specimen. The pendulum possesses kinetic energy and will continue to move until the energy has been dissipated. The recorded velocity will therefore be excessive by an amount depending upon the angular velocity of the pendulum at the moment of the break. This overthrow is greatest for small loads and can be corrected with lower rate of traverse. Now, let us see the balance principle. And so, the balance type of testers are based on principles of moments. As the name indicates, the principle is based on applying force on one side of a beam that holds the sample on other side, and while balancing the beam, it creates stress on the specimen and leads to breakage. So, let us consider a beam AB being pivoted at fulcrum point K. A force F is applied to the edge of the beam A at a distance of d1 from the fulcrum K. The beam is kept in equilibrium by the tension P developed in the specimen, which acts at a distance of d2 from the fulcrum point K. Since the sum of clockwise moments are equal to sum of anti-clockwise moments, and we can say that P into d2 is equal to F into d1. That means that the load on the specimen may be varied by changing the value of the force F or by changing the distance from the fulcrum at which a constant force F acts. Quite a few tensile testing machines are designed under the balance principle, and among them the Presley fiber strength tester and Denison T42F are worth mentioning. Then let us look at the principle of loading by springs. It is a simple principle of applying stress to the specimen by use of springs. An important property of the spring is the linear relationship which exists between the amount by which its initial stress has been changed and the force required to change. A helical spring is being used in some instruments and such as Cambridge extensometer. In the diagram shown, a helical spring S has a linear strain curve, and therefore, the tension developed in it is proportional to the extension. By extending the spring at a constant rate, a load may be applied at a constant rate. The specimen is gripped between the jaws G1 and G2. The upper grip G1 is connected to a leaf spring which has a restricted moment between the electrical contacts C1 and C2. The leaf spring is also connected to the helical spring. The upper end of the helical spring is clamped into a holder H1 which has a vertical moment controlled by the motor M1 driving a screwed rod R. The vertical moment of the grip 2 is controlled by the motor M2, and it is possible to test the specimens under both constant rate of loading and constant rate of extension conditions. To test under constant rate of loading conditions, the motor M1 runs continuously, the rate of loading being controlled by the speed of the rotation of the screwed rod and the stiffness of the spring. Motor M1 is switched on and the holder H1 moves upwards at a constant speed. The spring extends and the load is applied at a constant rate by doing so. The extension of the specimen causes the leaf spring to be deflected upwards and touch the upper contact C2. This switches on the motor M2, causing the lower grip H2 to move downwards for a shorter period and so take up the tension. The leaf spring is pulled off from the upper contact and the motor M2 is switched off. This cycle continues till the specimen breaks. So, the movement of the holder H1 provides the load applied and that of the holder H2 provide the extension. A suitable graphic device can be employed in order to get the load elongation curve by movement of these two holders. To test under constant rate of extension conditions, the motor M2 runs continuously, extending the specimen at a constant rate. The leaf spring is deflected downwards as the tension is developed in the specimen. When contact is made with C1, motor M1 switches on, extending the spring until the tension in it balances the tension in the specimen. The leaf spring is eventually pulled away from C1 and the motor M1 is switched off. Thus, the cycle of events continue till the specimen breaks. The Cambridge extensometer works under this principle, and this is one of the important testers that are being used in the industry today. Let us see the inclined plane principle, and this principle facilitates tensile testing based on constant rate of loading conditions. When you look at the figure now, the plane DB is a rail pivoted at K along with a heavy carriage C that can roll on the surface. The jaw J1 is a fixed jaw to the beam and J2 is a mobile jaw attached to the roll for gripping the specimen. The plane is tilted by dropping the end B, which causes heavy carriage to roll, thus creating tension in the sample. Tilting of the edge B continues till the specimen breaks. Here, let us consider the plane being inclined by sin theta to the horizontal. If the weight of the carriage is taken as W, that is acting downwards, then the force P acting on the material can be calculated by resolving the vertical force in two directions. One is parallel to the plane and the other perpendicular to the plane. Let P be the force parallel to the plane, that is force applied on the specimen, then P is equal to W to sin theta. Therefore, P is proportional to sin theta. Hence, the load on the specimen is directly proportional to the sine of the angle of inclination. The Scott serigraph used automatic single ion testers work under the principle of inclined plane. Then coming to the ballistic or impact principle, this facilitates measuring the work of rupture rather than the maximum load required to break the specimen, and therefore, the unit of measure is work of energy, that is, for example, it may be inch per pounds or it may be in joules. Results of the instruments based on this principle cannot be compared with the results from the instruments based on other principles. So, as shown in the figure drawing, a heavy pendulum is pivoted at A. The specimen grip J1 is a fixed jaw on the horizontal platform of the machine, and the specimen grip J2 is attached to the bob of the pendulum. Let G be the center of gravity of the pendulum and let W be its weight. Initially, the pendulum is in position 1 with the center of gravity at height h1 above the lowest point. The potential energy of the pendulum in this position is therefore W into h1 in lbs. When the pendulum is released, it swings downwards and when nearly vertical begins to pull on the specimen. Continuing its swing, the pendulum stretches the specimen, breaks it, rises to position 3 and finally coming to rest in position 2. The work required to break a specimen can be calculated by considering the height to which the center of gravity rises after break. Then let us think h2 be the height of a center of gravity above its lowest point. The potential energy in this position is W into h2, that is in lbs. Thus, the difference in the potential energies in position 1 and 3 is the energy or work required to break the specimen. Therefore, work of rupture is equal to W into h1 minus h2 inch lbs. Then let us look at strain gauge principle, and the strain gauge principle is based on measuring the changes in electrical resistance of the upper and lower planes of a flat spring as a result of changes that occur in its shape due to tensioning of a specimen till it breaks. In the given diagram, a stiff flat spring or beam is mounted as a cantilever. The upper jaw J1 is attached to the free end of the beam, and the lower jaw J2 has a controlled vertical movement through a screw mechanism. By moving J2 downwards, a tensile force is developed in the specimen which causes the free end of the beam to be deflected. The effects of the deflection are used to measure the magnitude of the load of the specimen. When the beam bends, the length of the upper face AB increases and the lower face CD decreases, and these changes in length being proportional to the load applied. The middle zone NL is not affected by the tension that is created. When a piece of resistance wire is stretched, its electrical resistance increases. Conversely, if it contracts, its resistance decreases. Further, the changes in the resistance value is proportional to the change in the length. When a resistance wire is attached to the upper and lower faces of the flat spring, changes that occur in electrical resistance by deflection of these planes is proportional to the load applied on the specimen. The visual recording is being done with a Wheatstone bridge, and which contains 4 resistances. Coming to the constant tension winding principle, it is a simple principle which is based on winding the yarn at a constant rate, subjecting it to higher tensions than the normal conditions of winding to obtain sufficient breaks. This test is closer to the practical winding and sometimes regarded as essential test for yarns subjected to further processing. And so, in this there are 2 small pulleys and one pulley which will be floating when the yarn is made to pass through. So, the tension, the weight of the pulley which is present in the center will provide tension on the yarn, and thus the breakage occurs wherever it is little weaker. And so, they generally they use more tension at this particular point, so that it breaks, and they look for certain breakages. And so, in order to make arrangements for further processing, they use this particular principle. Otherwise, this is not used for the other instruments, and so this is only used for the running yarn. Thus, we have seen today that there are many principles of tensile testing that underlie some of the instruments that are available today in the market for testing of the tensile properties of textiles. And all these instruments will be following one of the principles, and they will be made in order to test a textile, maybe in the form of a fiber, in the form of a fiber bundle, or maybe a yarn, or maybe in a leaf form, not a single yarn, in a leaf form or a fabric. The conditions in which the testing occurs may be it is constant rate of loading or constant rate of extension or constant rate of traverse. These machinery are available now with so many features today, and maybe some of the problems associated with these principles can be addressed by them without any problem. And some of these machinery are having another facility of getting a load elongation curve, and some of them are even connected with a microprocessor, so that there is no need of calculating some of the parameters that come up with the tensile loading.